My fabulous chemistry faithful. Last video of the unit, the organic reactions. Woohoo! There are 7 of these bad boys. I'm going to give you the basics and make sure we understand all of them. So, number one, probably most common and maybe my absolute favorite is combustion, i.e., fire. So, we need some things. We need a hydrocarbon of some source. That would be my fuel source. We need oxygen, and oxygen has to be on the reactant side, or this will not be a combustion. And combustion reactions always produce carbon dioxide and water. Since we're not in school, somebody remind me, and I'll probably post it up to the classroom like I normally wouldn't, but I can for us our sake because I can't do the whoosh bottle for you. Normally on this bell work day, I would do a demonstration and create fire for you. So here's an example of a hydrocarbon, methane, CH4. Methane is a burnable gas. Oxygen would be written as O2. Carbon dioxide, obviously, as CO2. And water, H2O. So there's an example of a combustion reaction. And balancing these things has always been, for me, fun because the number of carbons on both sides has to equal, and that's where you start. And it's challenging because oxygens are in 2 different molecules on the right-hand side, but I don't think we're going to get too much into that. There is a POGL on these guys to help you, I believe, understand these reactions a little bit better, a little bit more info. Otherwise, they're just kind of generic and you'd be able to see them. So addition and substitution are the next 2 really, really key ones. Addition needs a double bond. So you need to highlight that where it says atoms or groups are added at the double bond or triple bond. So I need an alkene or an alkyne. I need a double bond of some sort. And then we add it to a halogen, which is generally diatomic, right? Because most of the halogens are double diatomic. And I just create a halocarbon. I'm literally just going to break the double bond and add the halogen on. So here's an alkene. C2H4 is ethene. Halogen Br2, right? It could be Cl2, could be I2, could be F2. And then I'm just literally going to make one big halocarbon with 2 bromides on it. And here's an example of what's going on. So what I don't see is the plus. There should be a plus in between this C2H4 and the Br2. But the cool piece is that what I gave you an example matches this, right? Probably did that on purpose. Break that double bond in step 1. And then after the arrow for step 1, notice how I opened up some parking spots. And the parking spots are just going to go where the uh, the hydrogen should go, and the bromines just go in there. And then I have my halocarbon, which is a 1,2-dibromoethene. Okay. Substitution, very similar, but substitution happens now with a single bonded alkane. So now substitution swaps. Now I'm going to make a halocarbon and an acid. So I'll give you an example. C2H6, 6 hydrogens because it's single bonded. Add on the Br2, and now what happens is the substitution. An H and a Br switches. So one Br goes onto the molecule, and then the H comes off and goes to HBr, making the acid. So here's an example of that. So substitution happens when there is, on this example, of course, isn't exactly perfect. It matches your other example a little bit better. The Cl and an H literally just switch. They substitute each other. Okay, so this is like a double replacement reaction, except for it's a specific one based on organic molecules. Esterification, big word. Notice I'm just going to make an ester. So you need to know an organic acid and an alcohol makes an ester and water. The word for this is dehydration synthesis is the kind of reaction this is because I'm taking the water out. So I'm going to take the OH off of the acid, I believe, not just the H, and at least in the picture, that's how it shows. So here's a COO, an organic acid, added with an alcohol, and we learned about these functional groups yesterday, how there's a C double bonded to an O, then that C is bonded to an OH, that's the COO, and then an OH hydroxyl group, right? It's going to make an ester that's got a double bonded O and an inline O with an H2O water. So this is a dehydration synthesis. And in this picture, I'm taking off the OH off of the carboxylic acid, which is our, that's a common name for a particular kind of organic acid. We won't have to worry about that. You take the OH off of that, the H off of the alcohol, and you make the ester. I personally almost don't believe that. I would think the OH comes off the alcohol and the H comes off the hydrochloric acid because H's produce, but then we just have to see where everything lines up. But I think it would make the same molecule either way, and it would still be dehydration. Dehydration is them pulling water out of it, and they're highlighted in blue. You'll never be tested on which one actually loses the O, the alcohol or the acid. You'll never be tested on that, and that's kind of beyond the scope of our course, so no worries there. Saponification, this one's tough, but just remember soap. So saponification is looks like soap just reorganized. Move the O and you got soap. This is going to take an ester and a very strong base to make soap and glycerol. All you have to really remember is it makes soap. Very rarely do you even have to know that it's an ester and a base. Number one rule of Fight Club, we don't talk about Fight Club. Fermentation, also another good one. I take sugar, hit it with an enzyme, and I will make alcohol and carbon dioxide. Okay, so sugar, give it an enzyme, and I will produce an alcohol and CO2. So making alcohol is fermentation. That's how actually wine is made. Wine is fermented. Okay. Polymerization. This you can just take any kind of little notes in your polymerization place as you want. I might actually have these already put in there. You just need to know that polymerization and the picture on the right top will show you many monomers and then them linked together to make a polymer. Polymer means many, monomer means one. So if I just add them all together, this is a polymerization reaction. There aren't specific ones, so there's so many different ways to create a polymer out of little pieces where I just take lots of the same little pieces and match them up. So you just need to know lots of little pieces put together to make one big huge thing that is a polymerization. We call it growing chains because they literally just form bop, 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 and they line right up and then they get bigger and bigger. And we can control those reactions with temperature and time and pressure and things like that. And Kodak's actually really good at these things. At least they used to be back in the day. And with that, I think that's all 7. And that's the whole unit. We're done. This I believe this topic has a POGIL to make sure we cover these reactions a little bit more in depth. And that's it. You're on to Castle.